All right, ladies and gentlemen, welcome to today's lesson. This involves using the line of best fit and kind of interpreting things with your line of best fit. So you've been doing all these statistics, you're getting a lot of equations looking like this. We're just trying to decide, read more into the situation. And this requires some vocab. And the first couple here are independent and dependent variables. So an independent variable is a variable that changes regardless of other ones. Usually independent variables are things like time and how many people showed up to the event and how many hours you've been driving. I guess that's also time. So it's just kind of independent of what other things are happening. Typically things like time. Dependent variables are variables that, depend on another. How far you've driven will depend on how long you've been driving, or how old, your income is typically dependent on how long you've been working, and so those are dependent variable. When you're looking at situations, the X is typically the independent variable and Y is the dependent. It's just kind of a normal thing for us to do in our graphs. And that's how you'll be reading them in tables as well. The slope of your line of best fit is going to describe that number, say it's 11.48. That's how much the dependent variable goes up every time the independent goes up by 1. So your Y is going to increase some amount every time your X goes up by 1. And we'll see an example of what these kind of look like in context. The Y-intercept is the Y value when X is 0. So you're going to be pretty much writing these exact things, or this is what I'm looking for, except replace X and Y with what they represent in the situation, which you figure out when you figure out what the independent and dependent variables are. So let's look at a few examples from your assignment. So a lot of this is interpreting. You're not doing a lot of calculation on this assignment. So let's jump to this graph here. It has the amount spent on groceries, and then number of children. Well, the number of children are X, and typically X is our independent variable. Yeah, so we're going to have that number of children. All right. And then our dependent variable is going to be this Y here, which is the amount spent on groceries. And the reason the amount spent on groceries is dependent is because usually as the number of children people have in their family, the amount they spend on groceries goes up. Instead of the other way around. It's not like this couple is spending thousands and thousands of dollars on groceries and then they have a ton of children. It's not really how that works. Usually you buy more food because there's more people. And so that's why the amount spent on groceries is dependent in this case. Let me finish writing that. And then next one, what does the slope of the line mean in this context? So you got to look at your equation here. You got to find your slope, which is the number with the X variable when it's in slope-intercept form. So we got 21.08. That's 21.08 what? Is that 21.08 children or 21.08 in dollars spent on groceries? It's going to be dollars spent on groceries. Our X is number of children. So you take 21.8, you times by number of children, and that'll give you a dollar amount, okay? And so the 21.08 is spent per child, okay? Or every time the number of children goes up by 1, you can expect the amount of groceries to go up by $21.08. Right, so that's going back to these guidelines here, right? How much the Y increases when X goes up by 1. So if number of children goes up by 1, the amount spent on grocery goes up by 21.08. And then we got our next one. What does the Y-intercept mean in this context? The Y-intercept is here, and that's 85.15. And you think, is that number of children or amount spent on groceries? It's going to be the amount spent on groceries. So these numbers in here are going to represent Y values because Y equals those things on the right. The thing that's not amount spent on groceries is the X, which is number of children. And so this is going to be $85 and 15 cents when the x is 0. And so like, okay, well, when x is 0, well, x represents the number of children. So when the number of children is 0, that's the amount spent on groceries. So that's what we're going to write down. Is spent on groceries, is spent on groceries when there are no children. Which is sad, but, some people don't have any kids in their family, couples. Let's move to another one outside your assignment, and let's see if you can figure it out. All right, you fill these in, trying to do the interpretation. What's the independent variable? What's the dependent variable? Look at your slope on your equation, your line. What does that mean in the context? What's the y mean in the context? Go ahead and fill it in, and we'll have you check in a sec. All right, let's have you check and see how things went. Your independent variable, in this case, is going to be your meal cost, that first row there. The dependent variable is going to be the tip, right? People, when they go to restaurants, they'll leave a tip, at least in our country. And then the slope represents, the slope is 0.16, and that's how much the tip increases for each additional dollar spent on the meal. So when meal cost goes up $1, the tip is expected to go up 16 cents. And then the y-intercept represents a tip of negative 30 cents for a meal cost of 0, which sounds ridiculous, and that's true. But this brings up the important thing about statistics and these models, right, these lines of best fit, is there's a limitation on them. This is the mathematical line of best fit, but the line of best fit only works where you have data. If you look at your data set here, you'll notice there's nobody who has a meal cost of 0. And so our model only works when we have an actual meal cost that's similar to these ones. And so the model stops working when you go outside that data. That's called an extrapolation. Extrapolation, right? That's outside the data set, and so it's a prediction, and sometimes it might be off, right? Usually people don't come in, order nothing, and then the waiter or waitress gives them 30 cents. That's kind of ridiculous. We call those loiterers who come in and don't do anything. But, keep that in mind. This is what the line of best fit says, but you have to realize that sometimes things can be ridiculous if you go outside the data. And so there's another thing on your assignment you need to be able to do, and that's to be able to tell if the line of best fit actually matches the data, right? Remember when we had a scatter plot like this, and you can kind of sketch your quote-unquote line of best fit. Well, there are multiple lines you could have drawn, like we could have drawn a line like this, but that line doesn't match the data, right? We could have drawn a line like this. That line also doesn't represent the data very well. It's really bad at it, right? Any values on your line here are way off. Well, that's something you need to be able to recognize when you see a scatter plot and a line of quote-unquote best fit and see if it's good or not. Well, is this line of best fit a good fit for the data? And the answer for that's going to be no. This data is not following a linear progression. This is actually a type we've learned about in class called exponential. A line is not a good fit for an exponential. So this one's not that great, though, it kind of works in this section, but it doesn't work for the whole thing. Well, is this line a good fit for the data? Well, this one, it is going to be a good fit. Even though it's not a great fit, like it's decent, right? The data is going up. At least these bunches here. You have these on the outside that kind of give it just a blob sort of shape, but they're not. Most of the points are close to this line, and so it's the best fit we're going to get with a line. And so you can look at this. Is this a good fit for the data? Yeah, visually speaking, right, the points on your graph are close to your line of best fit. They follow the same pattern. So yeah, it's going to be a good fit. There's another example of a bad fit. It kind of comes down, comes back up. But It's okay. It's not the worst, but it's okay. This is a line of best fit. This is not a great fit, right? You got this bunch here that are above, bunch here down below, and they're not like evenly distributed around your line there. So this one's not that great. It doesn't follow the pattern of the data that well. Let's have you look at this one and figure out which would be a good line of best fit for this scatter plot, A, B, or C. If you pick B, good job. Yeah, this one goes in the middle. It follows the same pattern as the data. A doesn't even have the same sort of slope. C has the same slope, but it's above the points. And so if you're going to have a line of best fit, it's got to be going through the middle of your scatter plot, about the same amount above and below. So let's go to the last section here and answer a few questions about this. 15, visually, is this a good line of best fit for the data? Why or why not? This one's going to be no. It does not follow the same pattern as the data. The data's got a kind of an upside down U shape or a hill shape, and the line is, well, straight. So no, it's a terrible fit, and you should write that sort of stuff down. Next one, based on the line, the growth rate would be 8 when the temperature is 0, right? Like a temperature and the fish population growth rate. So we're looking at y-intercept here. Over here, population would be growing at a rate of 8 when the temperature is 0. What's wrong with that? If you know anything about water, at 0 degrees, water tends to be frozen. And it's really hard for things, like reproduce when the water's frozen. And I know there's, right, if you're like lakes and things like that, the top freezes and the bottoms, fish can still live there. But yeah, the fish are not really going to be growing when they're in an ice cube. And then, so yeah, that's something you can write down there. Sorry, I'm trying to finish so you can get through this. And then 17, according to the line, what is the growth rate when the temperature is 1,000? That's when you take your equation and you plug in 1,000. So you gotta do y equals 0.1 times 1,000 plus 8. Take a moment to put in your calculator. You should have gotten 108. And it's asking, what's wrong with that? A population growth rate of 108, that's doubling the amount of fish, more than doubling the amount of fish. The problem with that is at 1,000 degrees, that's like molten. The water disappears, it turns into water vapor. The fish are definitely not going to be like living at that temperature. And so, yeah, that's definitely a problem. And again, this is another example of an extrapolation, right? It's way outside the data set, definitely not going to be happening. And so there you go. Good luck on your assignment. Make sure you can tell if something's a good fit or not, and be able to tell what the independent and dependent variables are, and what the slope and y-intercept mean in context.